Welcome, everyone. Today, we're really getting down to basics, the absolute foundation if you're aiming to become an aviation maintenance technician.
That's right. We're jumping into Chapter 1 of the AMT Powerplant curriculum. This is the core stuff.
It really is. We're talking about the fundamental purpose of aircraft's engines. What they have to do to even be considered airworthy.
Exactly. We'll cover the must-have requirements, efficiency, reliability, durability, all that. And then we'll look at the big picture, the two main families, the piston engines and the gas turbines.
And importantly, how we measure their performance. It's not just about knowing the terms, but understanding why these things matter.
Absolutely. The goal today is to really unpack this first chapter, make it make sense beyond just the textbook definitions.
Okay, so where do we start? The absolute first principle has to be thrust, right? An airplane doesn't go anywhere without it.
Precisely. Thrust is that forward push the engine creates. In steady, level flight, it needs to exactly balance out the aerodynamic drag holding the aircraft back.
And this is where Newton comes in, his third law.
It's a perfect example. For every action, there's an equal and opposite reaction. The engine acts on a mass of air, throwing it backwards.
Action.
And the reaction is the air pushing the engine and therefore the aircraft forwards.
I think a lot of people get this slightly wrong. They imagine the engine pushing against the air behind the plane, like pushing off a wall.
Yeah, that's a common misconception. But it's not pushing against anything back there. It's about accelerating a mass rearward. The engine displaces air or combustion gases towards the tail.
The classic example helps here, the rocket in space.
Exactly. There's no air in space to push against, right? But a rocket generates enormous thrust.
Because it's throwing its own propellant, its own mass out the back at incredible speed.
That's it. Action throwing mass backward. Reaction rocket moves forward. It doesn't matter if it's propeller moving lots of air slowly or a jet engine moving less air very, very fast. Same principle, accelerate mass rearward.
Okay, that makes sense. It's about moving the working fluid, the air or the exhaust gases.
Correct. Whether it's a little Cessna or a giant A380, that fundamental physics doesn't change.
So with that foundation laid, let's talk about the rules engines have to play by. What are the non-negotiables when designing an aircraft engine?
Well, there are several key requirements that every single aircraft engine has to meet, legally and practically. They fall into a few main categories.
Okay.
First, you've got efficiency and economy. Efficiency means getting the most performance out of the fuel burned across all sorts of conditions.
And economy, is that just the purchase price?
Purchase price is part of it, sure. But for us as AMTs, a huge part of economy is the ongoing maintenance cost. An engine that's cheap to buy but costs a fortune to keep running isn't really economical. Our work directly impacts that.
Right. So efficiency in flight, economy over the lifespan. What else?
Then there's reliability. This is crucial. The engine has to produce its rated power consistently, even when things aren't perfect, bad weather, unusual attitudes, you name it. It has to keep running.
And closely related is durability, I imagine.
Very closely related, but distinct. Durability is about how long the engine can operate before it needs a major overhaul. We talk about time between overhauls, or TBO. It needs to last.
Reliability is will it fail unexpectedly? Durability is how long until planned major work.
That's a good way to put it. And both tie into the engine's power output capabilities, of course.
Okay, what about the physical engine itself? What constraints are designers working under?
Two big ones, weight and size. You always want a low weight to horsepower ratio. Every extra pound the engine weighs is a pound less of fuel or passengers or cargo the plane can carry.
So lower specific weight means better aircraft performance and payload.
Directly. And it needs to be compact. Space is always at a premium on an aircraft, whether it's under a cowling or slung under a wing.
And the final piece of the puzzle.
It has to handle a huge operating range. Think about it starting up in freezing temperatures, taking off on a hot day at high altitude, cruising efficiently way up high, taxiing on the ground. It has to perform reliably across all those different speeds, altitudes, and weather conditions.
That's a tall order. And those requirements really shape the kinds of engines we see today. Let's get into the two main families.
Broadly speaking, you have the reciprocating piston engines and the gas turbine engines.
Reciprocating, those are the ones most people picture in smaller planes.
Yeah, for general aviation, especially light aircraft, the horizontally opposed piston engine is king. Usually air-cooled, relatively simple, good economy for speeds under, say, 250 miles per hour.
What about those big round engines you see on old warbirds or maybe some agricultural planes? Radials.
Exactly, the radial engines. Powerful, very rugged designs. They used to power everything, but now they're pretty much limited to vintage aircraft, some older cargo planes, specialized ag sprayers. Their large frontal area creates a lot of drag, which isn't ideal for speed.
So for higher speeds, we move to the turbine family.
That's where the action is today. This family includes turboprops, where the turbine drives a propeller through a gearbox. Think regional airliners, some cargo planes. Then you have turbo shafts, which are very similar but primarily deliver power to a shaft, think helicopters, or the APUs, auxiliary power units, on larger jets.
And the ones powering the big airliners.
Those are almost all turbofans. These are incredibly efficient, especially at high speeds and altitudes. The big fan at the front moves a lot of air around the core engine.
And pure turbojets.
You still hear the term turbojet used sometimes as a general catch-all for any gas turbine engine, but pure turbojets, where all the air goes through the core. They're pretty rare now, except for some military applications or maybe older business jets. The turbofan just offers way better fuel economy for most flying.
So the choice really comes down to the mission, particularly the speed requirements.
Absolutely. It's all about efficiency zones. Below 250 mile-per-hour cruise, the piston engine is generally the most cost-effective and fuel-efficient.
And if you need to go a bit faster, carry more.
That's where the turboprop comes in, roughly in the 180 to 350 mile-per-hour range. It offers a much better power-to-weight ratio than a big piston engine, which is great for lifting heavier loads or for regional airline efficiency.
Then we hit that crossover point.
Right around 350, maybe 400 mile per hour. Above that, the turbofan takes over. They operate most efficiently at high subsonic speeds, say Mach 0.8 or 0.9, and high altitudes. This is your typical airline operation.
Why does the turboprop lose out at higher speeds?
Propeller efficiency starts to drop off significantly. The tips of the propeller blades approach supersonic speeds, creating shock waves and massive efficiency losses. The turbofan, moving air differently, doesn't have that same limitation.
And for supersonic flight?
Then you're talking pure turbojets, maybe with afterburners or low bypass military turbofans. Fuel economy takes a backseat to pure thrust and speed in that regime.
This ties perfectly into how we measure engine performance. Let's talk metrics. The first big difference is how we rate power, right?
Yeah, this trips up new students sometimes. Reciprocating engines are rated in brake horsepower, or BHP.
Okay, BHP.
That's the actual usable power delivered right at the propeller shaft after accounting for internal friction and losses. It's a measured value.
But gas turbines are different.
Gas turbines fundamentally produce thrust, measured in pounds. To compare them on a horsepower basis, we calculate thrust horsepower, or THP.
And there's a specific formula for THP, isn't there? It involves speed.
There is. The formula is 12 THP equals thrust times aircraft speed,
Oh, yeah.
375.55.
Thrust in pounds, speed in miles per hour. What's the 375?
That 375 constant comes directly from the definition of horsepower. 1 horsepower is 33,000 foot-pounds per minute. If you convert that to mile-pounds per hour, you get 375. It's just a conversion factor.
So unlike BHP, which is a relatively fixed rating for a given RPM, THP changes with airspeed.
Exactly, because speed is right there in the formula. A jet engine sitting still on the runway might be producing maximum thrust, but its thrust horsepower is 0 because the speed is 0.
Ah, okay. That makes sense. So THP has to be calculated for whatever speed the aircraft is actually flying at. Yeah.
Correct. That's why you often hear turbine engines referred to by their maximum static thrust rating, pounds of thrust when stationary, rather than a single horsepower figure. The horsepower output is dynamic.
Got it. Another important metric you mentioned earlier was weight. Let's talk specific weight.
Specific weight is simply the engine's weight divided by its power output, usually pounds per brake horsepower, pounds BHP.
And why is this so critical?
Because, like we said, every pound matters. An older engine might have a specific weight of, say, 2 pounds per horsepower. A modern turbofan might be down around 0.2 pounds per horsepower.
That's a huge difference.
Massive. And that difference translates directly into how much payload or fuel the aircraft can carry. Reducing specific weight has been a major driver of engine development for decades. It's all about giving the aircraft more useful load capability.
Makes sense.
Yeah.
Okay, let's shift to fuel economy. The key metric here is specific fuel consumption, or SFC.
Right. SFC tells you how efficiently the engine turns fuel into power or thrust. It's about how much fuel you burn per unit of output per hour.
And it's measured differently for turbines and piston engines.
Slightly, yes. For gas turbines, we use thrust-specific fuel consumption, TSFC. That's fuel flow, in pounds per hour, divided by the thrust produced in pounds.
Okay, LBRE per pound of thrust.
And for reciprocating engines, it's brake-specific fuel consumption, BSFC. That's fuel flow, pounds per hour, divided by the brake horsepower produced.
LBR year per bhp. And this SFC data backs up the speed discussion we had earlier.
It absolutely does. At lower speeds, a piston engine or a turboprop generally has a lower, meaning better, BSFC. They're more efficient down low.
But as speeds climb,
Above that 400 mile per hour mark or so, the turbofan's TSFC becomes better. Even though the core might be less efficient in isolation, the overall system, especially with that big bypass fan, becomes more efficient at moving the aircraft quickly through the air compared to a propeller fighting efficiency losses.
okay. Now, before we dive into the engine parts, there are two terms that are really important for AMTs to get right: durability and reliability. They sound similar, but they're not the same.
Not in our world, no. Reliability is really about the probability of the engine not failing unexpectedly. It's measured as the mean time between failures. This is largely baked in by the manufacturer through design, testing, and certification to meet FAA standards.
So reliability is inherent to design integrity. What's durability then?
Durability is about the engine's lifespan between scheduled overhauls, the time between overhauls, TBO. The manufacturer recommends a TBO, but the actual durability, how long that engine really lasts before needing that overhaul.
That depends on how it's used and maintained.
Exactly. It's heavily influenced by operating conditions, how much time spent at high power, high temperatures, and critically, the quality of the maintenance it receives. We, as AMTs, have a direct impact on an engine's durability. You can have a very reliable design that doesn't last its expected TBO because of poor upkeep.
That's a really key distinction for anyone working on these machines.
Yeah.
Okay, let's use that as a bridge. Time to look inside. We'll start with a reciprocating engine, the kind many AMTs will work on early in their careers. First up, cylinder arrangements.
The most common type you'll see in general aviation is the opposed engine, sometimes called an O-type or a boxer engine.
Opposed meaning.
Two banks of cylinders lying flat, directly opposite each other, sharing a central crankshaft. Think Subaru car engines, but scaled up and air-cooled, typically.
What are the advantages?
They have a very low profile, a narrow silhouette, which is great for fitting under cowlings, especially on twin-engine planes where they mount on the wings. They also have inherently good balance because the opposing pistons cancel out a lot of vibration.
And the other main type, historically.
The radial.
The radial engine. Cylinders arranged in a circle around a central crankcase. Could be a single row, 5, 7, or 9 cylinders usually, or double rows, sometimes even more, like 14 or even 28 cylinders on the really big ones, like the Pratt & Whitney R4360 Wasp Major.
Wow, why were they so popular?
Very good power-to-weight ratio for their time and incredibly rugged and dependable. But as we mentioned, that big round shape creates a lot of drag.
Okay, holding all this together is the foundation, the crankcase. What does it do? It's more than just a housing. It's the structural core. It has to support the crankshaft and the main bearings, provide strong mounting points for all the cylinders, resisting the immense force trying to blow them off during the power stroke, and it forms a tight enclosure for the lubrication system.
Must be incredibly strong. What's it made of?
Usually a high-strength aluminum alloy, either cast or forged. Aluminum is light and conducts heat well, which is vital. You'll see machine surfaces called cylinder pads where the cylinders bolt on, and heavy-duty mounting lugs used to attach the whole engine to the aircraft's firewall or engine mounts. It has to handle engine torque, vibration, and even gyroscopic forces from the propeller.
Inside the crankcase spins the crankshaft. Its job is fundamental.
Absolutely. It's the component that converts the up and down reciprocating motion of the pistons into the rotary motion needed to turn the propeller.
What are its main parts?
You have the main journals. These are the perfectly round sections that rest in the main bearing supported by the crankcase. Then you have the offset sections, the crank pins, where the connecting rods attach. The distance the crank pin is offset from the center line of the main journals determines the piston's stroke length. We call that offset the throw.
And connecting the journal to the pin.
That's the crank cheek or crank arm. It's the bridge between the main journal and the crank pin.
With all that mass spinning and changing direction, balance must be critical.
Oh, incredibly critical. Engines vibrate, and crankshafts are a major source. They undergo static balancing first, basically checking if the weight is evenly distributed when it's at rest, often done by placing it on knife edges.
But it also needs balancing when it's spinning.
Yes, that's dynamic balancing. This often involves dynamic dampers, which are clever little counterweights, almost like pendulums, attached to the crank cheeks. They're designed to oscillate slightly out of sync with the engine's natural torsional vibrations, effectively canceling them out. Without these, vibrations could literally shake the engine apart or cause serious airframe fatigue.
Wow. Okay, connecting the piston to that crank pin is the connecting rod.
Yep, the link in the chain. It transmits the huge combustion force from the piston down to the crankshaft. In opposed or inline engines, you typically have simple one-piece, plane-type connecting rods, one for each cylinder.
But radials are different, aren't they? Because all cylinders in a row share one crank pin.
Exactly. Radials use a master and articulated rod assembly. One cylinder in each row will have a very beefy master rod that connects directly to the crank pin. All the other connecting rods in that row, called articulated rods or link rods, pivot off the master rod via knuckle pins.
That sounds complex to assemble and time correctly.
It is. It means the geometry and stroke length aren't exactly identical for every piston in a radial row, which is something you have to account for in detailed analysis or overhaul.
Okay, let's move up to the piston itself. What's it made from?
Usually forged aluminum alloy. Strong, light, and good at handling heat. The top, the piston head, can be flat, convex, domed, or concave, depending on the engine design and compression ratio goals.
But there's a really clever design feature AMTs need to know about piston shape, isn't there? The cam ground piston.
Yes, this is crucial. Cam ground pistons are not perfectly round when they're cold. They are intentionally machined to be slightly oval, with the largest diameter perpendicular to the axis of the piston pin.
Why on earth would they do that? Seems counterintuitive.
Because metal expands when heated and pistons get very hot. The area around the piston pin bosses, where the pin goes through, is thicker and doesn't expand as much as the thinner piston skirt areas.
Ah, so if it was perfectly round when cold.
It would expand into an oval shape when hot, potentially binding in the cylinder bore or causing uneven way. By making it slightly oval when cold cam ground, it expands into a nearly perfect circle at normal operating temperatures.
That prevents it from sticking or slapping around in the cylinder, especially during warm-up.
Precisely. It ensures proper fit and minimizes wear across the operating temperature range. A really neat bit of engineering.
And on the piston, we find the piston rings. What types are there?
Typically, three main types sitting in grooves machined around the piston. At the top, you have the compression rings, usually 2 or 3 of these. Their job is to form a tight seal against the cylinder wall to prevent the high-pressure combustion gases from blowing past the piston into the crankcase. That's called blow-by.
Okay, seals the pressure in. What's next?
Below the compression rings are the oil control rings. These regulate the amount of lubricating oil on the cylinder walls. They scrape excess oil downwards, preventing it from getting up into the combustion chamber where it would burn and cause deposits or smoke. They often have slots or holes to allow the scraped oil to drain back through the piston to the crankcase.
And sometimes there's a third type.
Yes, often an oil scraper ring located near the bottom of the piston skirt. It's an extra line of defense to prevent excess oil from splashing up onto the cylinder walls.
Got it. Compression, oil control, oil scraping. Now, the structure they run inside the cylinder assembly, usually 2 main parts.
That's right. You have the cylinder barrel, which is the sleeve the piston moves up and down in. It's made from a very strong steel alloy forging.
And it must be incredibly wear resistant.
Absolutely. The inner surface has to withstand constant friction, heat, and pressure. To harden it, the bore is often nitrided. This is a chemical case hardening process where the steel is heated in an atmosphere of ammonia gas. Nitrogen atoms penetrate the surface, forming extremely hard iron nitrides, giving it fantastic wear resistance.
And attached to the barrel is the cylinder head.
Correct. The head is usually made of cast aluminum alloy because aluminum is excellent at dissipating heat. The head contains the combustion chamber recess, the spark plug bosses, and the passages and seats for the intake and exhaust valves.
How are the barrel and head joined? They experience huge forces and temperatures.
It's a critical joint. Often the aluminum head is heated up, expanding it, while the steel barrel might be chilled slightly. Then they are screwed together with very high torque. As they return to normal temperature, the head shrinks onto the barrel threads, creating an incredibly strong, gas-tight seal.
You can usually tell the exhaust side of the head just by looking.
Definitely. The exhaust valve and port run much hotter than the intake side, so you'll always see significantly more and deeper cooling fins cast into the aluminum around the exhaust area to help get rid of that extra heat.
Okay, before we talk about how it works, we need to know how to identify which cylinder is which. Orientation and numbering.
This is fundamental for maintenance. Rule number 1, the propeller end is always the front of the engine. Always.
Okay, prop end for front and left versus right.
You determine left and right by viewing the engine from the rear, looking forward from the accessory end.
Got it. Standing behind the engine, looking towards the prop. Now, how are they numbered? Let's start with opposed engines.
For opposed engines, unfortunately, there is no universal standard. Lycoming might number differently from Continental. You absolutely must check the specific engine's maintenance manual or the data plate. For example, one might call the right rear cylinder number 1, the left rear number 2, the right front number 3, the left front number 4, and so on. You just have to look it up. Don't guess.
Okay, always check the manual for opposed engines. What about radials? Is there a standard there?
Generally, yes, thankfully. For a single-row radial, viewing from the rear, the top cylinder is always number 1.
Top center is number 1.
Then numbering proceeds clockwise around the circle as viewed from the rear. So 1, 2, 3, 4, 5, and so on.
Simple enough. What about firing order? Does it just fire 1, 2, 3, 4, 5?
No, that would create terrible vibration. The firing order is designed to spread the power impulses evenly around the crankshaft rotation. For example, a 9-cylinder radial might fire 1, 3, 5, 7, 9, 2, 4, 6, 8. It jumps around to keep things smooth.
And double row radials. Gets more complex.
A bit. They usually have odd-numbered cylinders in one row, typically the rear, and even-numbered in the other row, the front. The firing order alternates between the rows to distribute power evenly. There are specific calculation methods, often involving adding or subtracting a fixed number, like add 9 or subtract 5 for a 14-cylinder, or add 11 subtract 7 for an 18-cylinder, to find the next cylinder in the sequence. Again, the manual is your absolute guide here.
Okay, manual is key for numbering and firing order. That precise firing is controlled by the valve train. Let's talk valves.
We use poppet valves, which look kind of like mushrooms or tulips. They pop open and close to let gases in and out of the cylinder.
Are intake and exhaust valves the same?
No, they live very different lives. Intake valves run relatively cool because they're constantly being cooled by the incoming fresh air-fuel mixture. They're often made of chrome-nickel steel alloys. Exhaust valves, however, have it rough. They have to withstand the direct blast of burning combustion gases, which can momentarily reach extreme temperatures, maybe 3,500, 4,000 degrees Fahrenheit, during the power stroke.
How do they possibly survive that?
They're made from highly heat-resistant superalloys like nichrome, or might have special coatings like stellate on the face where they seal against the seat. But the real lifesaver for many high-performance exhaust valves is internal cooling.
Internal cooling. How?
Many are sodium-filled. The valve stem is hollow and partially filled with metallic sodium.
Like the stuff in salt.
Well, metallic sodium, which is very reactive. When the engine heats up, the sodium melts into a liquid. As the valve bounces open and shut thousands of times a minute, this liquid sodium sloshes up and down inside the hollow stem.
And that carries heat away.
Exactly. Sodium is an excellent heat conductor. It picks up heat from the superhot valve head and transfers it down the stem, where the heat can then dissipate through the valve guide into the relatively cooler cylinder head and its cooling fins. This can lower the valve head temperature by hundreds of degrees. It's absolutely critical for durability in high-power engines.
It comes with a huge safety warning for AMTs.
A massive one. Metallic sodium reacts violently if exposed to air or moisture. It can cause fires or explosions. Under no circumstances should you ever try to cut open, grind, drill, or overheat a sodium-filled valve during maintenance or disposal in a way that could rupture the stem. Treat them with extreme caution. Check the manual to identify them.
Critical safety point.
Okay?
What makes the valves open and close at the right time?
That's the job of the camshaft and the lifters. The camshaft has lobes precisely shaped bumps that rotate. As the lobe comes around, it pushes on a valve lifter or tappet.
And there are different types of lifters.
Two main types: solid lifters and hydraulic lifters. Solid lifters are just solid pieces of metal. They require a specific small gap, called valve lash or tappet clearance, to be set between the lifter rocker arm and the valve stem when the engine is cold.
Why the gap?
To allow for thermal expansion. As the engine heats up, the valve stem and other parts grow slightly longer. Without that initial cold clearance, the valve might be held slightly open when hot, causing it to burn or lose compression. The downside is that this clearance needs to be periodically checked and adjusted as parts wear.
And hydraulic lifters, they solve that problem.
They do. Hydraulic lifters, also called zero-lash lifters, are more complex. They use engine oil pressure acting on an internal piston and check valve mechanism.
How does the oil help?
The lifter basically pumps itself up with oil, automatically expanding to take up all the clearance in the valve train, regardless of temperature or wear. The trapped column of oil acts like a solid link to open the valve, but it can bleed down slightly to allow the valve to fully close.
So no manual adjustments needed.
Correct. They automatically maintain zero lash, which reduces valve train noise, reduces maintenance requirements, and can slightly improve engine efficiency and longevity. Most modern opposed engines use hydraulic lifters.
Okay, that gives us a solid understanding of the parts. Now, let's put it all together in Section 4. How does the reciprocating engine actually operate? The four-stroke cycle.
Right, often called the Otto cycle after Nicholas Otto. It takes 4 strokes of the piston, 2 up, 2 down, which requires 2 complete revolutions of the crankshaft, 720 degrees, to complete 1 full power cycle per cylinder.
5 events happen: intake, compression, ignition, power, exhaust. Let's start with intake. Piston moves down.
Piston moves down, creating suction. But the intake valve doesn't just pop open at the top dead center, TDC. It actually opens a few degrees before TDC. This is called valve lead.
Why open early?
To get the flow started. And it doesn't close right when the piston hits the bottom dead center, BDC, either. It stays open for quite a few degrees after BDC. This is valve lag.
And the reason for lag?
Inertia. The air-fuel mixture rushing into the cylinder has momentum. Even as the piston starts back up, that momentum continues to pack more mixture into the cylinder for a short time. This lead and lag maximizes the amount of charge crammed in, which we call improving volumetric efficiency.
Okay, so intake fills the cylinder, then compression.
Piston moves up, both valves are closed now, squeezing that air-fuel mixture into a much smaller volume in the combustion chamber. This raises its pressure and temperature dramatically.
Then, before the piston even reaches the top, ignition.
Right. The spark plug fires well before TDC, typically somewhere between 20 and 35 degrees BTDC.
Why so early? Seems like it would push against the rising piston.
Because combustion isn't instantaneous, it takes a fraction of a second for the flame front to spread across the chamber and build up pressure. Firing early ensures that peak pressure occurs just after the piston passes TDC and is starting its way down on the power stroke, giving it the strongest possible push.
The power stroke, that's where the work gets done. You mentioned huge forces earlier.
Immense forces. The rapidly expanding hot gases can slam the piston down, with forces equivalent to 15 tons or more in large aircraft engines. This force is transmitted through the connecting rod to turn the crankshaft.
And the exhaust valve opens early too.
Yes, similar to the intake valve lag, the exhaust valve opens significantly before BDC on the power stroke, maybe 50 to 75 degrees early. This is called exhaust lead. It allows the high residual pressure in the cylinder to start blowing down the exhaust system before the piston has to waste energy pushing it out on the upstroke.
Okay, so power stroke ends, piston starts up for the exhaust stroke.
Piston moves up, pushing the remaining burned gases out through the open exhaust valve.
And then there's that period where both valves are open slightly.
Right at the end of the exhaust stroke and the beginning of the intake stroke, there's a brief period called valve overlap, where both the intake and exhaust valves are open simultaneously for a few degrees of crankshaft rotation.
Why have overlap? Seems risky.
It's carefully timed. The outflowing exhaust gases help create a slight suction effect that pulls the fresh intake charge into the cylinder more effectively, a process called scavenging. It helps clear out all the burnt gases and get a full charge for the next cycle. It also helps cool the exhaust valves slightly.
Okay, intake, compression, power, exhaust, 720 degrees. Now, a key parameter related to the compression stroke is the compression ratio.
Defined simply as the ratio of the cylinder volume when the piston is at the bottom, BDC, to the volume when the piston is at the top, TDC. So at 8.1 compression ratio means the volume at BDC is 8 times larger than the volume at TDC.
Higher compression generally means more power and better efficiency, right?
Up to a point, yes. But there's a major limiting factor: abnormal combustion.
You mean detonation and pre-ignition?
Exactly. These are killers for engines. Pre-ignition is when something in the cylinder, maybe a hot spot on a spark plug electrode or a carbon deposit, gets glowing hot and ignites the fuel-air mixture before the spark plug fires. This can cause damage because it fights the piston coming up.
Oh, detonation.
Detonation is even more destructive. It happens after the spark plug fires normally. The initial flame front starts spreading, but it compresses the remaining unburned mixture, the N gas, ahead of it, to the point where that N gas spontaneously explodes violently, rather than burning smoothly.
Like a tiny bomb going off inside the cylinder.
Precisely. It creates massive, instantaneous pressure spikes and shock waves. You might hear it as a sharp, metallic knocking or pinging sound. Detonation can destroy pistons, rings, and cylinder heads very quickly. High compression ratios, high power settings, high manifold pressure, and incorrect fuel grade or ignition timing all increase the risk.
Something AMTs need to be very aware of during operation and troubleshooting. Okay, Let's clarify the different types of horsepower we talk about. Start with the theoretical maximum, indicated horsepower, IHP.
IHP is the power actually developed inside the cylinders by the burning gas pressure acting on the pistons. It's a calculated value, not directly measured at the shaft. We calculate it based on the average pressure inside the cylinder during the power stroke, called the indicated mean effective pressure, IMEP.
Is there a formula for that?
Yes, the classic P-Lang formula is often used as a mnemonic for students. YHP equals P times L times A times N times K,
Yeah.
$33,000.
Okay, break down P-length for us.
P is the IMEP, pressure in PSI. L is the length of the piston stroke in feet. A is the piston head area in square inches. N is the number of power strokes per minute per cylinder, which is RPM2 for a four-stroke engine. And K is the number of cylinders. Divide all that by 33,000, the FT argument in 1 horsepower to get IHP. It's the theoretical power generated internally.
But that's not the power we get out because of friction.
Correct. We lose some power just overcoming the internal friction of the engine pistons rubbing against cylinders, bearings spinning, gears meshing, plus the energy needed to pump air in and out and drive accessories like oil pumps and magnetos. This lost power is called friction horsepower, FHP.
How much power is lost to friction?
Typically around 10 to 15% of the indicated horsepower.
So if we take the theoretical power, IHP, and subtract the friction losses, FHP, we get
The actual usable power delivered to the propeller shaft, brake horsepower, BHP. So by HP equals IHP FHP2.
and BHP is measurable.
Yes.
Okay.
It's measured externally using a device like a dynamometer, often called a dyno or a brake, hence brake horsepower. The dyno measures the engine's torque, twisting force, at a given RPM, and horsepower is calculated from torque and RPM using the formula. Y VHPL, torque times RPM, 52522.
Okay, so BHP is the number we really care about for performance. Let's quickly touch on engine efficiencies. First, thermal efficiency.
Thermal efficiency is about how well the engine converts the chemical energy stored in the fuel into useful mechanical work, BHP. Unfortunately, internal combustion engines are not very good at this.
How bad are we talking?
Typical reciprocating aircraft engines might only achieve around 30 to 34% thermal efficiency. Most of the fuel's energy is wasted.
Where does the rest go?
A huge chunk, maybe 40 to 45%, goes right out the exhaust pipe as waste heat. Another significant portion is lost to the cooling system, whether air or liquid cooling. Only about a third actually becomes useful power. Managing that waste heat is a huge challenge.
Okay, what about mechanical efficiency?
Mechanical efficiency is the ratio of the output power, BHP, to the internal power, IHP. So mechanical efficiency is BHP, IHP2. It tells us how much of the power generated in the cylinders actually makes it to the propeller shaft after friction losses.
And that's usually pretty high.
Yes, much better than thermal efficiency. Modern engines can reach mechanical efficiencies approaching 90%, especially near their rated power output.
And finally, volumetric efficiency. We mentioned this with valve timing.
Right. Volumetric efficiency compares the actual volume of air-fuel mixture drawn into the cylinder during the intake stroke to the theoretical maximum volume the cylinder could hold, the piston displacement.
So ideally, you'd want 100%. Fill it completely.
Ideally, yes. But in a normally aspirated engine, one without a turbocharger or supercharger, it's usually less than 100%. Things like intake manifold restrictions, air filter drag, valve timing compromises, and high cylinder head temperatures can all reduce the amount of charge that actually gets inducted. Running at part throttle significantly reduces it too.
But you can get over 100%.
Yes, if the engine is turbocharged or supercharged, these systems force air into the engine at pressures above atmospheric pressure, effectively packing more air mass and fuel into the same cylinder volume. That's how you can get volumetric efficiencies exceeding 100%, leading to significantly more power output.
Okay, that wraps up the reciprocating engine fundamentals. Let's shift gears completely now to the gas turbine world. What's the biggest difference in how they operate?
The fundamental difference is the continuous flow cycle. Unlike a piston engine where intake, compression, combustion, and exhaust happen sequentially in the same cylinder, a gas turbine does all these things simultaneously and continuously in different sections of the engine.
So air is always flowing through it.
Constantly. Air comes in the front, gets compressed, fuel is added and burned, the hot gas spins a turbine, and then it exits out the back. All happening at the same time in different places.
Let's walk through those sections. Inlet, compressor.
Combustor, turbine, and exhaust. That's the basic flow path.
But modern airliner engines, the big turbofans, have more complexity like spools.
Right. Most large turbofans are dual spool or sometimes even triple spool engines. Think of it like having two or three separate rotating assemblies nested inside each other, spinning at different speeds.
What does each spool drive?
Typically, you have a low pressure spool, often called N1, which consists of the large fan at the front, some initial compressor stages, low pressure compressor, and the final turbine stages, low pressure turbine that drive it. Then you have a separate high pressure spool, N2, which includes the main high pressure compressor stages and the first hottest turbine stages, high pressure turbine, that drive the high pressure compressor.
Why the different souls?
It allows each section, fan, low pressure compressor, high pressure compressor, to rotate at its own optimal speed for maximum efficiency, which you couldn't achieve if everything was bolted to a single shaft.
And that big fan at the front is key to efficiency, right? The bypass ratio.
Absolutely critical for modern airliners. The bypass ratio compares the amount of air that goes around the core engine through the bypass duct pushed by the fan to the amount of air that goes through the core, compressor, combustor, turbine.
And in high bypass engines, most of the air goes around.
Yes. Bypass ratios can be 5.1, 10.1, even higher on the newest engines. This means 10 times more air might be going around the core than through it.
Where does the thrust come from then?
The vast majority of the thrust, sometimes up to 80% or more, comes from that relatively cool, slower-moving air being accelerated by the big fan. The hot, high-velocity jet exhaust from the core provides the rest. It's much more fuel-efficient to move a large mass of air slowly, like the fan does, than a small mass of air very quickly, like a pure turbojet core.
Okay, let's look at the compressor section. Its job is to squeeze the incoming air. Two main types.
Yes, centrifugal flow and axial flow.
Centrifugal first. How does it work?
It uses a spinning impeller, which looks a bit like a fan with curved blades. Air comes into the center, gets slung outwards at high speed by the impeller's rotation. Then it passes through a stationary diffuser section, which slows the air down and converts its velocity energy into pressure energy.
Advantages and disadvantages.
They're simple, rugged, and can produce a relatively high pressure rise in a single stage, maybe 8.1 or more. But they have a large frontal diameter, which creates drag, so they're mostly used in smaller engines like turboprops, turboshafts, helicopters, APUs, or older turbojets.
And the other type, standard on bigger engines.
The axial flow compressor. This is the type you see on virtually all large turbofans and turbojets. Air flows generally parallel to the axis of the engine straight through.
How does it build pressure?
It uses multiple stages. Each stage consists of a row of rotating blades, rotors, followed by a row of stationary blades, stators. The rotors accelerate the air, adding kinetic energy. The stators then act like diffusers, slowing the air down slightly and converting that kinetic energy into a pressure increase.
You just stack these stages up.
Exactly. By passing the air through many stages, sometimes 10, 15, even more, you can achieve very high overall pressure ratios, like 40.1 or even higher on advanced engines, while keeping the engine diameter relatively slim for better aerodynamics.
Now, something important for AMTs working around turbine engines is bleed air. Where does that come from?
Bleed air is hot, high-pressure air tapped directly from various stages within the compressor section.
And what's it used for? Sounds important.
It's vital for the aircraft. We use it for cabin pressurization and air conditioning. It's used for anti-icing critical surfaces like the engine inlet cowls and wing leading edges. It can power pneumatic systems, start other engines, and even run things like vortex dissipators on some engines to prevent FOB ingestion on the ground. It's a crucial resource bled off the engine's compressor.
Okay, so highly compressed air leaves the compressor and heads towards the combustion section. But the air is moving really fast now, isn't it?
Extremely fast.
Yeah.
Too fast for stable combustion. So the first thing it encounters after the compressor is another diffuser section.
What does this diffuser do?
Its job is to slow down that high-velocity compressor discharge air significantly, converting more of its kinetic energy into static pressure. You need relatively slow-moving air entering the combustion chamber itself, otherwise the flame would just get blown right out the back.
Makes sense. Then into the combustion chamber or combustor can.
Right. This is where fuel is mixed with the air and burned continuously. It's a carefully designed chamber, often an annular ring-shaped design in modern engines, or sometimes individual cans or a can-annular combination.
What are the key jobs of the combustor?
Three main things. Mix fuel and air efficiently, garn that mixture completely with minimal pressure loss, and crucially cool the resulting super hot gases before they reach the turbine.
How hot does it get in there?
The core flame temperature can briefly reach 3,500 degrees Fahrenheit or even more. That's hotter than the melting point of the metals downstream.
So how does it cool the gases down?
Only a portion of the air entering the combustor section, called primary air, is used directly for combustion. The rest, the secondary air, is carefully routed through holes and passages in the combustor liner. This cooler secondary air mixes with the combustion products, diluting and cooling them down rapidly to a temperature the turbine can withstand, typically around 1500 to maybe 2500 degrees Fahrenheit at the turbine inlet, depending on the engine.
Still incredibly hot, but manageable for the turbine alloys. Okay, those hot, high-pressure gases now blast into the turbine section. What's its job?
The turbine's job is to extract energy from that hot, high-velocity gas stream and convert it back into mechanical energy shaft power,
To drive what?
primarily to drive the compressor sections. Remember, compressing all that air takes a huge amount of energy. The turbine has to extract enough power to keep the compressor spinning. It also drives the engine accessories, fuel pumps, generators, hydraulic pumps, via a gearbox.
How much energy does the turbine extract just to run the compressor?
A surprisingly large amount, often somewhere between 60 and 70% of all the energy released by burning the fuel is needed just to drive the compressor. Only the remaining energy is available to produce thrust, either directly as jet exhaust or by driving the fan propeller.
Wow. What are the main parts of the turbine section?
Similar to the axial compressor, it usually consists of stationary turbine inlet guide vanes, also called nozzle guide vanes or turbine stators, followed by rotating turbine disc wheels with blades attached.
Which part is the hottest?
The very first row of stationary nozzle guide vanes, right at the turbine inlet. They take the direct hit from the combustor exit gases and are typically the hottest components in the entire engine. They accelerate the gas and direct it onto the first stage turbine blades at the optimal angle.
And the rotating turbine blades? They
Yeah.
must be under incredible stress.
Extreme stress, huge centrifugal forces trying to pull them off the disc, plus those incredibly high temperatures. They're made from exotic nickel-based superalloys and are often single crystal castings to eliminate grain boundaries that could be weak points.
How are they attached?
Usually with intricate interlocking fir tree roots that slide into matching slots in the turbine disc rim, this distributes the load effectively.
And cooling, is that needed here too?
Absolutely essential, especially for the high-pressure turbine blades and vanes. Many are actually hollow, and relatively cool bleed air from the compressor is ducted inside the vanes and blades. It flows through complex internal passages and exits through tiny holes drilled in the leading edge, trailing edge, or surface, creating a film of cooler air that insulates the metal from the hottest gases. It's incredibly sophisticated cooling technology.
Amazing. Okay, let's wrap up with Section 6. Gas turbine operation principles and performance. The underlying thermodynamic cycle isn't Otto, it's...
It's the Brayton cycle, named after George Brayton. It's characterized by continuous combustion at constant pressure. Unlike the Otto cycle's intermittent constant volume combustion, the four processes, intake, compression, combustion, heat addition at constant pressure, expansion through the turbine and nozzle, and exhaust, all happen continuously and simultaneously in different parts of the engine.
We talked about thrust being action-reaction.
Yeah.
How does Newton's second law apply more specifically to jet thrust?
The common formula used is one equals is 5m's V2 V1, where 5m is the net thrust. V to all is the mass airflow through the engine, mass per second. V to cols is the exit velocity of the gas stream, and V to 1 is the inlet velocity, basically the aircraft speed. G is just the gravitational constant to keep units consistent.
So thrust comes from accelerating the air mass by increasing its velocity from V to 1 to V to 1.
That's the essence of it. You increase thrust either by increasing the mass airflow, which is what high bypass fans are great at, or by increasing the exit velocity, V palpable,
Yeah.
which is what pure turbojets do, or a combination of both.
Okay, let's talk thermal performance. What really drives the efficiency of a gas turbine?
Three main factors are most critical. Number one is turbine inlet temperature, TIT. The hotter you can run the gases entering the turbine, the more energy is available and the higher the potential thermal efficiency. This is why engine designers constantly push the limits of materials technology to allow higher TITs. The trade-off is that higher temperatures reduce engine life and durability.
Makes sense. What are the other two factors?
Second is the compression ratio. Higher compression ratios lead to higher thermal efficiency, just like in piston engines. This is directly related to how fast the compressor spins, its RPM. Third is the component efficiency, is how effectively the compressor compresses the air and how effectively the turbine extracts energy from the gas stream without excessive losses. Small improvements here add up.
Now, crucially for pilots and AMTs, how does the environment affect engine performance? Let's start with outside air temperature, OAT.
OAT has a huge effect. Thrust increases significantly as OAT decreases. Cold air is denser.
Denser air means more mass entering the engine per revolution.
Exactly. More mass flow means more thrust. Also, when the air is colder, the compressor doesn't have to work quite as hard, use as much energy, to achieve the desired pressure ratio, leaving more energy available for producing thrust. Cold days are great for turbine engine performance. Hot days reduce thrust available for takeoff.
Okay, what about altitude?
Altitude is a double-edged sword. As you climb, the air gets colder, which is good for the reasons we just discussed. However, the air also gets significantly less dense.
And the density effect wins.
Yes. The decrease in air density as you climb has a much larger negative impact on mass airflow than the positive effect of the colder temperature. So, net thrust decreases as altitude increases. Engines produce less thrust up high than they do at sea level, even though it's colder.
Finally, what about airspeed? How does the aircraft's speed affect the thrust the engine produces? You mentioned ram recovery.
This one is a bit counterintuitive at first. As an aircraft accelerates from zero speed, the net thrust initially decreases slightly.
Why?
Because the inlet velocity, $1 in the formula, is increasing. This reduces the difference between the exit velocity, $V, and the inlet velocity, $V, slightly reducing the calculated net thrust, $V, V.
But then it starts to increase.
Yes. As airspeed builds up further, the effect of ram recovery becomes dominant. The forward motion of the aircraft literally rams more air into the engine inlet. This increases the pressure and density of the air entering the compressor, significantly boosting the mass airflow. This increased mass flow more than compensates for the smaller velocity difference, causing the net thrust to increase quite substantially as the aircraft accelerates towards its cruising speed, up until effects near the speed of sound start to limit things.
Okay, that ram effect is powerful. So
Okay.
we've covered a lot of ground today, really digging into the fundamentals from Chapter
Yeah.
1. We went from Newton's laws defining thrust.
All the way through the essential requirements every engine must meet: reliability, durability, efficiency, economy, low weight.
We compared the two main families, reciprocating and gas turbine, looked at their specific applications based on speed.
And then got into the nitty-gritty of how they work internally. Things like cam-ground pistons and sodium-filled valves in recip engines.
And compressors, combustors, turbines, spools, and bypass ratios in the turbines. Plus, the key metrics like BHP, THP, SFC, and the efficiencies.
And we finished with how gas turbines perform, the Brayton cycle, and those critical environmental effects: temperature, altitude, and airspeed.
It really underscores that these machines are built on fundamental principles, but they operate under incredible stress.
That's right. We talked about reliability and durability being designed in by the manufacturer. They build these things to incredibly high standards through design and testing.
But as the source material points out, keeping them reliable, ensuring they actually reach that design durability, or TBO, that falls heavily on the people who operate and maintain them.
Absolutely. The engineering is amazing, but it needs the support of skilled maintenance. When you think about the forces 15 tons on a piston head, or turbine blades glowing red hot just shy of melting, spinning at tens of thousands of RPM, you realize how critical careful maintenance is.
So for everyone listening, especially those of you starting your AMT journey, here's something to think about as you learn more. We've seen the complexity, the high temperatures, the immense pressures. We know the manufacturer builds in reliability. But continued reliability and achieving that full TBO depends on maintenance. Given what we've discussed, the difference between a solid and hydraulic lifter, the criticality of cooling, the dangers of detonation, what specific maintenance practices or checks, beyond just following the schedule, will you prioritize to ensure these incredibly stressed systems make it safely through another cycle? What details will you focus on to uphold the durability the designers intended?
It's that attention to detail, understanding the why behind the procedures, that makes a great AMT.
Exactly. Keep that question in mind as you continue your studies. Thanks for joining us for this deep dive.